Right gang, it's new topic time. So this is the bit you've all been waiting for that I really dread because it's kind of boring. So we're on to the space stuff. This video, I'm going to throw a lot of facts at you. Hopefully you already know a lot of them, so I'm going to go relatively quickly because conceptually there's not a lot difficult in this, there's just a lot of stuff to learn. Stuff you need to know. Contents of the universe, life cycle of stars, and the characteristics of white dwarfs, neutron stars and black holes. So that last bit's the slightly harder bit, the rest of this you probably know already. Or hopefully some of you do, and we can just whiz through these. So just to make sure that we've got some of our key terms and that we're using words correctly, let's start with the Milky Way. The Milky Way is our galaxy. The trope is that the reason it's called that is because it looks like milk spilt across the sky, so they called it the Milky Way. Although it's quite hard to see it because obviously we're looking through it, so you have to get it looking exactly right. There are obviously lots of galaxies. Galaxies are made up of billions of stars all bound together by gravity. There are thought to be at least 200 billion galaxies in our universe, each containing on average 2 billion stars. So that's Andromeda for you. And this just shows you where we are in the Milky Way. Any of you who are Douglas Adams fans may be happy of saying that it's on the western spiral arm of the galaxy, a small insignificant blue-green planet that we are. If you're not a Douglas Adams fan, don't panic. You don't need to know it in any detail like that. So that's galaxies which are inside the universe. Please don't mix those up. And then we have stars. So stars are basically massive luminous balls of gas, once again held together by gravity. Our star, the Sun, is a very bog standard, boring, unexciting star. It's pretty run-of-the-mill really, if anything it's kind of small. It's about 75% hydrogen, 24% helium and 1% other things, so things like carbon and oxygen. And there are about, as I've said, around 2 billion stars in our galaxy. Stars come in different colours, and the colours tell us things about them, and we will actually talk about this more later, but just to give you an idea, it mostly depends on the surface temperature. So our Sun is a yellow star, which puts it about here. So red stars are the cool ones, blue and white stars are the very hot ones. So just to give you an example, one of the brightest stars in the night sky is Sirius, and that is a blue-white star. So, life cycle of a star then. Stars start as nebula, and the nebulae come together. They're mostly hydrogen and small amounts of other dust, and they just get pulled together by gravity. Because of that gravitational attraction, the gas and the dust clumps together. The gravitational potential energy, so as they lose that gravitational potential energy, as they get pulled in, that gets converted into heat, so it starts to get hot and it starts to glow. Once it's glowing, it is called a protostar, arbitrary picture. These are inside nebulae, so they're not very easy to see. So, once it gets hot enough, we start to get nuclear fusion. So temperature needs to be around 10 million degrees C at the core of the star, and the hydrogen nuclei get joined together and they fuse to form helium. Now, thing I want to highlight, I said hydrogen nuclei, not atoms. There are definitely not electrons associated with those protons. They are nuclei. So the hydrogen nuclei form helium nuclei. That's a way to lose marks if you don't remember that. And that is nuclear fusion, which we will talk about more later. Doing that releases energy. As the star undergoes nuclear fusion, it produces something called radiation pressure, which is basically an outward pressure. So we've got gravity pulling in, and we've got the radiation pressure pushing out. And those two will balance each other. When they're balanced, you find a stable star that's not changing size. Over the course of a star's life, those forces can become unbalanced and the star will then change size. And we'll talk about that a little bit more. So it's just a little illustration to show you part of the way that we get towards getting helium. We have to go via some isotopes of hydrogen, so deuterium and tritium can be used to then pump out our helium and an extra neutron. So, solar systems then. So when our star formed, it started as a nebula, and about 99.9% of the mass of that nebula made the star, made our sun, and the 0.1% that was left over made all the other stuff in our solar system. So there's the planets, but there's also the asteroid belts, there's some comets that have got some erratic orbits. Literally everything else was the 0.1% that was left over. So I hope you're feeling kind of insignificant now. That's kind of what space stuff does. So that's where our planets came from. Anyway, I'm assuming you all know the order of the planets. I doubt they'll ever ask you, but you know, my very easy method just speeds up naming, because Pluto isn't a planet. So currently our sun is in what we call the main sequence, and it's about halfway through that, and that process takes about 10 billion years. At this point, it's just the hydrogen that's being burnt, or inverted commas burnt, fused inside the core of the star through the nuclear fusion. So basically in our star at the minute, we've got some helium that's been made, that's just not doing anything, it's just sat there. Then we've got a little bundle of hydrogen, which is what is fusing, and then we've got all the rest of the gas that's floating around, the other stuff that's not quite made it into the core. Over time, the sun is going to get hotter. So in about 2 billion years, life on Earth won't be possible because the sun's going to be too hot, so we're going to be outside the Goldilocks zone. So, you know, let's start planning. Only 2 billion years to go. Now, once all the hydrogen is gone, the fusion's basically going to stop. Because there's no more hydrogen to fuse, so that pressure that was pushing out is going to stop. But the gravity will still be there, so the star is going to collapse in on itself. As it collapses, that gravitational energy is going to get converted into heat anymore. It's going to get even hotter. Now, our star is big enough that that means that the helium, that ash that was in the middle, is now going to be able to fuse because the temperature is increased inside the star. So we now start to have helium being fused, and it starts to form those heavier elements, and this is where they come from. But now that I'm fusing helium, I've now got a radiation pressure again, and it's going to be a really big radiation pressure. It's going to be bigger than when it was hydrogen. So that means that the star is going to get much, much bigger. At this point it gets called a red giant. Now, those of you who are eagle-eyed may note that when it was in the main sequence our sun is yellow, but when it becomes a red giant it becomes red. I know, shocking. But yellow stars are hotter than red stars, but I said that now that it's fusing helium, it's hotter. And that's because it's got a much bigger surface area that temperature is spread over. So the surface is actually cooler, which is why it's a red giant, even though at the core it is burning an awful lot hotter. Okay. Now when our star does become a red giant, it's going to pretty much engulf the Earth. So that just gives you an idea of the scale. So this is the sun now, and that's how big it would be when it becomes a red giant. Okay, right, so red giant fusing helium. Once the helium's all gone, then that's kind of it. It's going to collapse again, our star, and it's just going to form a very hot and dense object that will be about the size of the Earth, and it's called a white dwarf. So, key features. We wanted characteristics of white dwarfs. Hot, dense object, and it is the final stage in a sun-sized star. It comes after the main sequence, after the red giant. It's just the core of the star that's left over, and it is only the core that forms the white dwarf, because all the outer layers sort of blow away and they form a new planetary nebula, which could, you know, lead to the birth of a new star. The cycle continues. And as a little note, eventually the white dwarfs are going to cool down, and once they cool down, they form black dwarfs. So, a little bit more detail about white dwarfs, because this is something that they have now explicitly put into the syllabus, so I'm going to explicitly tell you it. So, after the red giant stage, we said that there's no more radiation pressure, so the star starts to collapse. But it doesn't collapse endlessly, it stops, and it stops because of something called electron degeneracy. Now, those of you doing chemistry should be familiar with the Pauli exclusion principle. The Pauli exclusion principle says that no two electrons can be in the same state. So even though they want to be in the lowest energy state, I can't have two electrons in exactly the same state. So basically, as my star shrinks, the electrons get pushed into the lowest energy states possible, but we can't push multiple to be together, and that basically provides a quantum mechanical pushback. What you need to remember is that the collapse is halted because of electron degeneracy. It just stops it getting any smaller. Now, this depends on the mass, because obviously I said that the gravitational pressure isn't enough to overcome this. And the limit for the mass of a star that can do this is called the Chandrasekhar limit. I have no idea if I'm saying that right, but that is how it is spelt. I suggest it could be a term to learn how to spell, because if I were an evil examiner, I might ask you a question with a QWC mark and maybe expect you to use that word. And if you did use that word, you would need to use it correctly. Okay, so that is the story for bog standard stars like our Sun. Nebula, protostar, main sequence, red giant, white dwarf with a planetary nebula. High mass stars do other stuff. Most of the stars that we can see are much more massive than the Sun, and I do mean massive. They have more mass, so they are therefore often brighter. So that's Orion. I don't know if you can spot it. So there's his belt. Got some legs. I never know where the bow goes, but that's Orion. These stars, these higher mass stars, when we compare them to the Sun, they are bigger, brighter, bluer when they're in the main sequence, and they pass through their life cycles more quickly, and they can end their lives differently. So high mass stars burn brighter but burn faster. It's basically what it boils down to. They do the same nebula, protostar, main sequence. They just tend to be bluer when they're in the main sequence, so hotter. After they're done with the main sequence, they don't become red giants, they become red supergiants. And in these red supergiants, we don't just see helium fusing, we also see carbon and oxygen undergoing nuclear fusion, which is how we can make the heaviest things we see in the universe, the heaviest stable things we see in the universe anyway. All the way up to iron can be made inside these red supergiants. And Betelgeuse is an example of a star that is doing this. So as you can see, as we get further out, we get the lighter things being fused, but we do see much more elements being fused rather than just the helium. And that's what makes it the red supergiant. So after the red supergiant is done, it goes supernova. So basically, once it reaches a point where it is hot enough to make the iron fuse, we get kind of basically an implosion. So iron is the most stable thing, so to make it fuse you put in energy rather than get out energy, and basically we kind of get energy going in and then out, and it all rebounds. We get a huge big explosion that lasts for days and days and days, and that's called a supernova. They're pretty rare. The last documented one that was seen was in 1604. Now when I say they're rare, I think I was reading a thing that there are about one happening every 4 seconds in the entire universe. But because the universe is so big, we don't see them. There's no way to predict when they're going to happen. But if they do, what happens in our lifetime, you will probably remember it, because it should be pretty stunning if it's anywhere near us. Okay, and there's just an example of a nebula that was left over after a supernova that was seen in 1054. Right, so after supernova there's two options, and we need to know about both these options because they are neutron stars or black holes. So let's start with neutron stars. The neutron star is where the core of the star is left over after the supernova, and the gravity is large enough that electrons and protons combine to form neutrons, which is why it's called a neutron star. Now these neutron stars are tiny, like we're talking 10 kilometers in diameter, but unbelievably dense. So lovely example there, teaspoon of neutron star is 2 billion tons. So pretty big. Basically these are really, really dense, and they form neutrons inside them because of their gravitational pressure. And so Sometimes they emit regular radio signals and they're called pulsars, but you don't explicitly need to know about them. Right, next up, black holes. So after the supernova, if the core that's left over is really massive, then instead of a neutron star, we get a black hole. Black holes basically have so much mass that their gravity is so strong that nothing can escape the pull of that gravity, not even light, which is why they appear dark. And we can only observe them, therefore, because of the effect they have on their surroundings. Okay, so basically our sun, pretty boring, is born protostar in a nebula, going through its main sequence now. This is where we are. Eventually it'll become a red giant. It'll then cast off a planetary nebula and become a white dwarf. So it's not going to go supernova, it's not going to go red supergiant, it will not be a neutron star or a black hole. So just to kind of clear it up in your mind, I've got a little diagram for you. So stars start as a nebula. Now if they're particularly low mass, so this is talking about the core of the star, if it's less than 0.015 times the core of our sun, it will fail and it'll just become a hunk of rock known as a brown dwarf. If it's bigger than that, it'll go to a protostar and it'll go into the main sequence. The ones that are less than our sun will just go off and become white dwarfs. The ones that are, you know, anything from 0.23 to 4 times the mass of ours will go to a red giant and then emit a planetary nebula as they become a white dwarf. If they are more than 4 times, if their core is more than 4 times the mass of the core of our sun, they'll become a red supergiant. If the core of that is less than 1.4 times the core of our sun, then it'll just become a planetary nebula. If it's greater than that, it will go supernova and will then either, if it is a relatively light star, become a neutron star. If it's a very, very massive star, it will become a black hole. So you need to get your head around that and be able to recite it, basically. Should be pretty straightforward, but learn it, basically. So I'm just going to talk a little bit about how sun elements are formed, and then we're nearly done. So hydrogen and helium. Hydrogen and some helium were formed at the original Big Bang. We call the ratios of them, or we call the presence of them as being primordial helium. We're going to come back to that a little bit later, so try and stick that phrase in your head. Primordial helium is helium that was created during the Big Bang. Helium is also made by fusion inside main sequence stars. The lighter end of elements, so other than hydrogen and helium, so we're talking carbon, oxygen, silicon, that sort of stuff, those are formed in red giants. But the heaviest elements come from, the heaviest element you get from red supergiants are going to be iron. We can't get any heavier than iron. Any element that is heavier than iron, must have been formed during a supernova, because that's the only place that it could have been formed. So the fact that we have elements heavier than iron on Earth prove that all the atoms that make up the Earth must have come from another star previously. In fact, they must have come from another supernova. So there is a song that I can't remember by who that has the lyric, "We are all made of stars." And that is actually scientifically accurate. We are made up of the remnants of exploded dead stars. So hopefully that makes you feel a bit more special than how insignificant we are. So that's a lot of information. You need to digest it, and this is the bit you're not going to like, you need to be able to use it to answer long questions in the exam. So you may want to bring your notes to next lesson, because guess what we're going to be doing? Right, any questions? Ask me when you see me.